Well, hello modeling. So today we're going to be going through the rest of the guided notes that we would have done in class. Please be sure that you have the actual paper so you can write down the guided notes because as you requested, the assignment to upload it is going to be right here on Canvas. And then also have open the graph that we worked on in class together in Desmos. Make sure that you are logged in so that you can open up the saved graph. If you have not made this yet, then you can use your guided notes and actually type in the temperature and ice cream sales into a table into Desmos. You can do that by clicking this plus button and then adding a table and then typing in each of the data values. Effective learning from a video means that you can pause, rewind, and fast forward as well. So if you need to type that in, do so now. And otherwise, let's get started. Where we left off on earlier this week is that we identified the x and the y values for our tables. We identified that the x value is the temperature, the y value is the ice cream sales, which makes the x value the independent variable, and the y value the dependent variable. Now, historically, students were asked to make a scatter plot by actually putting it on a piece of paper, but we're taking advantage of our technology. We're taking advantage of Desmos. And so when we look at our graph right here, we are trying to identify what sort of relationship does it have. It's going to be a linear relationship. It looks like that these are pretty much in a straight line with some variation because it's real life. So is this a strong or a weak correlation? Is it positive or is it negative? First, to identify what correlation means, if it is correlated, it means that it is related but not causational, right? Ice cream sales may go up in the summer, but so do shark attacks. Do shark attacks happen because we sold more ice cream cones? No, those are two correlated things because the temperature went up. And so here we can say with confidence that this is a strong linear correlation. It looks like a straight line. Is it the strongest? No. These lines could be more collinear. They could be more in a straight line, but it is still a strong correlation. And is it positive or negative? Well, as we go up on our x value, we're going up on our y value, which means that it is a positive relationship as well. Now, in order to create a best fit line, we're going to use Desmos to do that. And we'll be able to take advantage of typing in an equation a very specific way to use this tool. First, we're going to be using the variables that are identified in our table. I have x1 and y1. If you made the table the first time, you should also see x1 and y1, but there's occasionally a student who will have x2 and y2 here. You want to make sure that your variable you type matches your table, otherwise it doesn't work. So here I'm going to type y, and then to get that subscript, I'm doing the underscore button, so shift underscore, then typing a 1, and then I want to make sure I leave this subscript. So I'm going to click the arrow button to go over to leave the subscript. Otherwise, you end up typing in the subscript, and then that's just not going to work, right? So make sure you leave that subscript with the arrow button, and then we're going to put the tilde button. And that's what you're going to find in the top left-hand corner by the escape key. That's going to replace the equal sign for our equation, for our y equals mx plus b. That means approximation because we're going to approximate this y1 and x1 data table. So now, what variable represents slope? M. What variable represents their independent values? The x. Make sure you put the subscript of 1 on there as well. And you'll notice it immediately generated a line, but we're not done yet because we do need to put our b value, y equals mx plus b. And now we have an equation. Now we have our slope-intercept form, our line of best fit for this data made by Desmos. I want to point out, in case you haven't used Desmos before, you can change the colors. So if you're like, I want this to be a different color, you can make that to your preference. So I'm going to leave it as blue and purple here. So what we can see here is that this doesn't just give us a line, but it gives us our values for our line. And so our value of m, our slope, means it's rise over run. And so this slope of 16.34, and I'll write that here, 16.34, means that for every 1 we go up on our x, for every 1 degree we increase in our temperature, we're increasing 16 on our y. We're increasing $16. So we can make a prediction that when we go up by 2 degrees, we're going to be making $32 more. Our b value we'll talk about later on in these notes, but I'll go ahead and mark the b value here. So we have negative 674.827. And so for our equation here, we can just type that in. We have y is equal to the 16.34. Oops, my x is in the wrong spot. Let's fix that. The 16.34x minus that y value of 674.827. So that is our equation for our best fit line. Y equals mx plus b. Y equals 16.34x minus 674.827. So what does this do for us? What is the purpose of our best fit line? How does it help us with our real life data? Well, that's where this vocabulary for residual comes in. The residual is how far away, which is the difference, right? That's what the word difference means. It's how different the actual y coordinate of our data is versus what we would predict it to be. So like I just said, with a slope of 16.34, I would expect that for every 2 degrees we go up, we'd make an extra $32. Does that actually happen all the time? Of course not. So the residual tells us how far away we are from that expected value. And so in order to get that residual number, we're going to take the actual value and subtract it from the predicted value. So what I'm going to ask you to do now is actually do that calculation. Pick any 2 points you want on this graph and subtract them and write the residual down. If, for example, I pick this point right here, 59.4 and 332, that is the actual value. That goes in the first place. The predicted value is the value on your line of best fit. You can find that by clicking and dragging on your line. So you would click and drag until you get to 59.4. It's finicky, it's touchy, so you want to make sure that you're being really intentional and careful. But here you go, 59.4. Come on, get there, get there. So 59.4, the predicted value is 296.163. The actual value is 332. So my residual is 332 minus 296.163. So you're welcome to use that example. You're welcome to pick a different example, but please go ahead and find not just 1 point, but 2 points and calculate the residual. Pause if you need to take a moment in order to do that, but otherwise, we're going to go to the next part of the guided notes. So, what does it mean for the residual to be positive, and how does it compare with the line of best fit? A positive residual means the actual value is above the line. That's what this example here showed. 332 is more than that 200 value that was on our line. So a positive value means when we subtract, the actual value was larger than our prediction. If it was negative, it would mean it's below our line of best fit. So our actual value is less than our line of best fit. What does it mean if the residual is close to 0? Well, if you have a residual close to 0, it means that the actual value and the predicted value aren't that different. And if there's not a big difference, it means it's actually really close to the line. So a residual close to 0 means the actual value is close to the predicted value, right? And of course, conversely, if it's far from 0, it's going to be far from the predicted value. And so that's where now, if we were doing this on paper, we would take each of our points, subtract it from the line, and get our residual plot. We would find out how far away are each of these values, and we would be able to graph that on a plot. So here though, because we're using technology, we don't need to do this by hand. And to make the residual plot, you may have already noticed that Desmos actually labels it right here as residuals, and it gives you a fancy button, plot. If you click this, you cannot undo it. So once you click it, it's a permanent choice. So I'm going to go ahead and click plot, boom. And you'll notice it added another graph up here on our table. And those are the residual values. And you'll also notice it is not the difference of 57.6 and 215. Instead, it's actually looking at that 215 value for the actual Y value right here, 185, and subtracting that from the value that's going to be ended up on the graph itself to get that result. So what happens now? Well, what happens now is you may have noticed that as soon as I zoomed out on my graph, that we have these collection of points down here. Now you'll notice that that's not up here with the rest of the graph. That's down here a ways, and the reason why is because it's actually the difference that we're looking for. So this was only 13 different, and it's negative. So this point is 13 below where it would have ended up on the line. 185 is right around 13 below that 100 and the 200 value, if I were to get it to match up perfect. So what do those residuals do? Well, the residuals tell us a lot, actually. First off, if this was not a line of best fit, meaning that this graph wasn't actually linear, if the best way to estimate it, the best fit line, wasn't a straight line, then these residuals would show a pattern. These residuals would either show a smiley face pattern like a curve, they would show a pattern that's going up and down, they would show some sort of predictable pattern because the line of best fit, if it is truly a line of best fit, then your data would be essentially random. Real life isn't that predictable. So a line of best fit would have residuals that look random. And so, do these look random? Absolutely. I can't tell a predictable pattern with any of these dots. And so, that informs me that this is a linear model and that this is the best line to fit our data. Now, the y-intercept represents a predicted value when the x value is 0, right? In case you forgot, when we look at our x value, it's going to be 0 to get our y-intercept right over here. Now, in order to get that y-intercept, we can actually click it on the graph, but you'll notice that that y-intercept matches our b value because y equals mx plus b. B is the y-intercept, so I don't need to go all the way to the graph here. I can stay looking at my graph and my residuals here. And so what is the y value for our line of best fit? The y value for our line of best fit is identified here in our equation, this negative 674.827. Now, what does that mean in the context of our data? Right? We always want to ask when we're looking at a model if it actually makes sense. And so this is a y value, and the y value is cost. It's money. And the x value is temperature. So when the x is 0, we have a temperature of 0. That's possible, right? We can have a temperature of 0 degrees, especially if we're talking about 0 degrees Fahrenheit. But does it make sense in the cost of our data? And the answer is that since the y value is how much money we lose, if the temperature is 0, then no, not really, right? It doesn't make sense that we're going to lose $674 if we go to sell ice cream when it's 0 degrees. Unless we have like the cost of our truck or the cost of our business costing us $674 a day, this does not make sense. So when we talk about where our model works, we want to be specific to our model existing in certain places and recognize when our model doesn't work so we can create a new model for those other circumstances. So here, our model is only in between 41 degrees and 110 degrees. Otherwise, we won't go and sell ice cream if it's less than 41 degrees outside, right? If our model says we won't make money if we're going out when it's less than 41 degrees, then we're not going to go out and sell ice cream. So our model doesn't work, right? And in that case, we can now go to that last question. We can use the line of best fit to make a prediction. If it's 85 degrees outside, how much do you think we'd make on ice cream sales? I am not clicking on any of the dots on the graph because I'm not looking for the actual value. I want to know the predicted value. So the predicted value means we're going to go to 85. And so I'm continuing to click and drag. So you notice my cursor is actually a little bit off of the line itself because I clicked on the line and then I'm dragging it over. And once I hit to 85, and here we go. At 85, we have 714.63 cents with the 757, right? So let me go ahead and type that in here. 714.63757. So 714 point, oh, I immediately lost it here. Let me go back. 714.63757. 63757. Now, that is the value that we pulled off the graph, but how much money does that actually make? Remember, money is in dollars and cents, and there's not enough common sense in the world, so be sure to be kind with one another. But we'd want to make sure we round this to not 63, but instead the 7 makes our 3 round up, so we'd go 714.64. And so, ladies and gentlemen, that concludes our guided notes. At this point, you now have all the tools to look at our assignment for this week, our analyzing linear regression. Here it's going to give you another data set and ask you a variety of questions about analyzing that data set. Before you click on analyzing linear regression, don't forget to upload your notes in the guided notes assignment. So, thank you. Hope you have a wonderful afternoon, and I look forward to seeing you soon.